Every single time you read a prompt, you're plugging into decades of incredible innovation. So in this explainer, we're going to pull back the curtain on that history, starting with simple word prediction, ending up at the sophisticated art of prompting we use today. Let's dive in.
Okay, so we've all been there, right? You type a question into a chat box, hit enter, and magic happens. But what's actually going on under the hood? I mean, really, getting a handle on this is the absolute key to becoming a master prompter, whether you're building products, designing experiences, or running a business. All right, let's just boil it all down. At its very heart, no matter how complicated it seems, a large language model is really just a super-powered prediction engine. Its entire purpose in life is to look at a string of words and make the best possible guess for what word comes next. That's it. That one simple idea is the bedrock for everything else we're about to talk about. So how did we get from that simple idea to where we are now? Well, the journey didn't start with some grand quest for artificial consciousness or anything like that. Nope, it started with something way simpler: brute force statistics. The very first language models were basically just really, really good accountants for words. This first crack at the problem was called an n-gram model. Just imagine reading billions of sentences. If the model sees the phrase, "the cat sat on the," it literally just counts up what word most often comes next in all the text it's ever seen. Is it mat? Is it chair? It's just a game of raw probability, looking only at a tiny window of the last couple of words. Super simple, but for its time, it was a start.
But, and it's a big but, here's the problem. Take a look at this. This was actually generated by an early model that only looked at the previous two words. Any little chunk of 2 or 3 words kind of makes sense on its own, right? But the whole sentence, it's complete and utter gibberish. It has no long-term memory, zero concept of the bigger picture. And that's really the core issue.
N-grams were essentially looking at language through a tiny little keyhole. They could see the two words right in front of them, but they had absolutely no idea what was said 10 words ago, let alone at the top of the page. They could fake grammar in tiny bursts, but they couldn't produce a single coherent thought. So just counting words was never going to be enough. For AI to take the next big step, it needed a massive breakthrough. It had to go beyond just looking at the sequence of words and start to actually grasp what the words mean. This was the great pivot. We stopped asking, how often does this word follow that word? And we started asking a much deeper question. How are the meanings of these words related to each other? And answering that question, well, it required a completely new way of representing language itself. The solution was brilliant: word embeddings. I want you to think of it like giving every single word in a language its own set of GPS coordinates. But instead of a map of the world, it's a map of meaning. Words stop being just letters and become points in a mathematical space. And the really cool part? The distance between any 2 points tells you how similar their meanings are. This creates this incredible meaning map. So on this map, you'd find words like cherry and strawberry hanging out right next to each other because they show up in similar contexts. But a word like digital, that's going to be in a totally different zip code, way on the other side of the map. All of a sudden, language isn't just words anymore. It's geometry. And boom, here is our first huge insight for better prompting. This is exactly why you don't need to hunt for the one perfect keyword. You can say car or automobile or vehicle, and the model gets it. Why? Because on that meaning map, all those words are clustered together in the same neighborhood. You're not aiming for a single point. You're pointing the model to a whole region of meaning. Okay, so word embeddings gave models a sense of meaning, which is huge, but they still had the memory of a goldfish when it came to long-term context. And solving that problem led to the next revolution, an architecture that literally powers every single AI you use today, the transformer. This was the million-dollar question, right? If you feed a model a 10-page document and ask it a question about the first paragraph, how on earth does it know which words from the very beginning are still relevant at the very end? The earlier models, they just forget. The answer was a groundbreaking idea called the attention mechanism. And it's just what it sounds like. It gives the model the ability to look at an entire ocean of text all at once And for every new word it's about to generate, it can decide which of the previous words, all of them, are the most important to pay attention to. This is how it connects a pronoun at the very end of a document to a name mentioned on page 1.
A really easy way to think about it is like this. For every word it's working on, the model asks itself a little question, a query, like, what info do I need right now? Then it scans all the other words in the text, the keys, looking for potential clues. Finally, it grabs the most relevant bits of information, the values, and uses them to make its next word prediction. It's like a super fast research assistant.
But of course, attention isn't the whole shebang. It's one absolutely critical piece inside a way bigger and more complex machine. Think of it this way. Modern models don't just have one of these attention layers. They stack dozens and dozens of them, one on top of the other, creating this incredibly powerful, multi-layered system for understanding language. So here's our next crucial takeaway for prompting. Attention is the superpower that lets you feed the model a massive block of text with background, examples, rules, whatever you want. The model has the power to find the signal in the noise and connect the dots no matter how far apart they are. This means the way you structure your prompt directly tells the model what it should pay attention to. So, a brilliant architecture is one thing, but the real jaw-dropping magic, that started to happen when we combine the transformer with one more ingredient. Just unbelievable, mind-boggling scale. Just take a second and look at that number. 405 billion. That's the number of parameters. You can think of them as tiny little tunable knobs inside a model like Llama 3. During training, every single one of those 405 billion knobs is being adjusted and readjusted, all to get just a tiny bit better at that one core job, predicting the next word. And the scale of the data it learns from is just as wild. These models aren't just trained on one type of text. They learn from this huge, diverse diet of information. Like this dataset, the Pile, which has everything from academic papers and books to websites and conversations. It's this incredible diversity that gives them such a broad understanding of the world. Now, this is where things get really fascinating. When you combine that powerful transformer architecture with that massive scale, something totally unexpected happens. The models start to develop what we call emergent abilities. These are skills they were never explicitly programmed to do. Things like learning from just a handful of examples, or reasoning through a problem step by step, or following really complex instructions. They just emerge. And that brings us full circle. From the dead simple act of predicting one word, all the way to the sophisticated art of prompting. Everything we've just walked through builds up to this very moment. So when we look at modern prompting techniques like few-shot learning or chain of thought, you have to realize they aren't commands in the old-school sense. They're actually carefully constructed contexts. When you provide a few examples or show the model how to think step by step, you're not ordering it around. You're setting up a pattern. You're masterfully guiding its prediction engine to continue that pattern in a way that solves your exact problem. So if you remember one thing, let it be this. When you write a prompt, you're not commanding a machine. You're guiding a world-class prediction engine. You're carefully curating the input, setting the stage for what it's going to predict next. So the real question is, now that you know how it all works, what are you going to have it predict?